Hello, my name is David Gloria, and I am presenting my KIN 515 Cap 2 assignment, The Fate of Lactate. On the right is a diagram of those major steps and pathways of lactate. And so I'll go ahead and explain what that is and what that means. So under anaerobic condition, glucose goes through a process we call glycolysis. And in that process, glucose splits into two pyruvate molecules. Also in that process, two NADH and two ATP molecules are formed and actually attach to those pyruvate molecules, which then in turn produces or converts into lactate. Between the pyruvate and lactate conversion, it's important to note that there is a step or a bridge that comes via the LDH enzyme or the lactate dehydrogenase enzyme, again, which is a kind of a middle step in between pyruvate and the actual conversion of lactate. Once lactate is produced in the muscle, it is then taken into the bloodstream and then taken into the liver. And once that lactate is in the liver, the reverse process then happens. Lactate via the LDH enzyme converts back into pyruvate. Pyruvate through a process we call gluconeogenesis converts back into glucose. And once glucose has been formed or produced, it is now ready to go back into the bloodstream and taken up into the muscle. So the muscle can then go ahead and repeat the cycle all over again. And so those are just some of the major steps and pathways of lactate. Now that pathway can be affected by a number of things, but in speaking today, exercise intensity and duration are what we'll be discussing and how those pathways are affected. So if you took a low to moderate exercise with a low to moderate intensity or a steady state exercise, we're going to find that little to zero lactate will accumulate in the blood. Remember that middle section of that diagram. There's not going to be a whole lot. That cycle is just going to keep going regularly without any interruptions. However, as physical activity increases, and especially in intensity, blood lactate will begin to increase and eventually will accumulate in the blood. If we continue in a higher intensity exercise, where the intensity continues to grow, our blood lactate will actually reach a 2.5 millimole value, which will take us to what we call the lactate threshold. Again, if we continue in that exercise mode of high intensity and duration, our blood lactate value will reach a 4.0 millimole value, which we call onset of blood lactate accumulation, or OBLA. Once we reach OBLA, this indicates that there is an increase in glycolysis to meet the energy demands of exercise intensity. So again, in the steady state, low to moderate intensity, there's no disruption. The cycle is going along fine, but it is when the exercise intensity begins to increase that we begin to see blood lactate increase and accumulation. We get to the OBLA, and now we are requiring the body to meet its energy demands of the exercise intensity that we're at. So just if you looked at two athletes, if you looked at an untrained athlete, they're probably going to reach their OBLA much quicker than a trained athlete. Because the longer it takes an athlete to reach their OBLA by way of higher O2 consumption, this generally is going to indicate a greater overall performance. And so important to know, really, as exercise intensity increases, blood lactate will also increase and accumulation will begin to increase. Lactate versus lactic acid. Quickly here, lactic acid and lactate are two different things. They're not really interchangeable, even though a lot of people may use them synonymously in lectures or in just explaining to people what they are. But it's important to know that lactic acid is just that. It's an acid that is formed during anaerobic glycolysis. So we saw the diagram, we saw the glycolysis process. Well, lactic acid is being formed in that process. Then what lactic acid does is it releases hydrogen ions that attach to pyruvate via the LDH enzyme, which then converts into lactate. So lactate is a product of lactic acid in a nutshell. So it's just important to know that lactic acid, lactate, two different things. One's a product of the other. One's an acid, one is not. So anyway, that's that on that topic. Moving on to lactate metabolically and consequences of lactate accumulation. So lactate is not just a waste product that is a very bad thing or a negative thing that many researchers in the past hypothesized. What we have found through more diligent research is that lactate is a good thing because it can be used as a source of energy with increased physical exercise. And I think the key here is to remember that when sufficient and adequate supplies of oxygen present themselves, oxygen can use glucose and or glycogen as a fuel source. And I think that's the main key, sufficient and adequate supply of oxygen. This is when lactate can be used as a catalyst for energy or a source of energy in increased physical exercise. Now, some of the consequences of lactate accumulation. When our blood lactate accumulation falls below a 7.0 pH, and we'll talk about that in the next slide, this produces states of acidosis, or our bodies are now in an acidic state as a result of lactate accumulation in the blood. And the consequences of that, if that is not regulated, is nausea, headache, dizziness, and even slight to very severe pain in our muscles in muscle activity. So those are some of the consequences, so to speak, of lactate accumulation. Which takes us to our final topic for this presentation, which is acid buffering. We mentioned pH just a little bit, and basically what pH is, it refers to the measure of acidity or alkalinity in our blood, okay, or in a liquid solution. And so we know that a 7.4 pH is neutral, is normal for acid-base regulation. That's where we generally want to be and we want to stay at. However, through high-intensity exercise, vigorous exercise, the body, with blood accumulation, blood lactate accumulation increasing in our blood, that has the potential to put us in a state of acidosis or in a more acidic state. And so there are three ways that the body regulates pH. And that quickly is through chemical buffering, ventilatory buffering, and renal buffering. And so chemical buffering, by example, let's take the example of bicarbonate buffering. What that does is, that is when hydrochloric acid converts to carbonic acid, combining with sodium bicarbonate to produce a slight reduction in pH. It's often referred to as the first line of defense in regulating a pH, chemical buffering. That is why there is a ventilatory buffering as well as a renal buffering. And ventilatory buffering is when our lungs help remove excess CO2, carbon dioxide, from the blood. And renal buffering is the removal of HCO3 from the body. So as you can see, there are three different ways in which our bodies help to regulate acid, whether we slip into an acidic state, acidosis, or a more alkaline state, alkalinity. The chemical, ventilatory, and renal buffering aid in bringing us back to a neutral pH. So here are the references for this video presentation, and this is the conclusion of my CAP2 assignment, Fate of Lactate video presentation. Thank you, and God bless.